Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. My contributions to computer science that made the news headlines in 1989 were these. I discovered how to record the fastest computer speeds and how to do so by computing across an ensemble of the slowest processors in the world. I discovered how to leapfrog from slowest processors to fastest computers. The fastest supercomputer in the world is the heavyweight champion of the computer world. Beyond the fastest supercomputer is an unknown field of knowledge or a place where chaos begs to be replaced with order, darkness by light, ugliness by beauty, and ignorance by knowledge. I discovered how to leapfrog from the slowest processors to the fastest computers, solving problems at the speed limit. I discovered how to solve the most compute-intensive problems in mathematics and science and solve them with the slowest processors. I discovered how to make the most with the least. The eureka moment or high point of my parallel supercomputer quest for the fastest computer in the world occurred at 15 minutes after 8 in the morning of July 4, 1989, in Los Alamos, New Mexico, USA. And it occurred within my ensemble of the slowest 65,536 processors. In 1989, I was in the news for providing the quote-unquote final proof that supercomputing across millions of processors is not science fiction. In theory, mathematical predictions that were governed by a system of partial differential equations that encoded some laws of physics should be as reliable as a hammer. But in practice, it's a different story. The fastest computer in the world shortens the gap between theory and practice. In a world without the fastest computers, the solutions of the most compute-intensive mathematical problems, such as the simulation of long-term climate change, will be as approximate as a sketch instead of as exact as a photograph. The implication of my discovery of the first world's fastest computing executed across the world's slowest processors was far-reaching. My invention made the news headlines because the world's fastest computer is an enabling technology that enables us to discover new knowledge and unknown materials and create never before seen products. My contribution to computer science is this. I was in the news because I was the first person to use the slowest processors to discover the fastest computing and solve the most compute-intensive problems. To invent is to create something from nothing or make the fictional factual. The discovery is a time machine that takes us to the past to see a thing that pre-existed but remained unseen. The invention enables us to create our future. Genius is the ability to see what others saw as a rock and see it as a diamond. I achieved a milestone in the history of the computer. On July 4, 1989, the supercomputing community marked my milestone as the first time the world's fastest computer speed was recorded across the world's slowest processors. In supercomputing, the perennial question was how to discover the fastest speeds and use them to make the impossible to solve mathematical problems possible to solve. Before my discovery of the world's fastest computer, which occurred on July 4, 1989, how to solve the most compute-intensive mathematical problems wasn't known to any mathematician, wasn't taught in any mathematics course, and wasn't written in any mathematics textbook. Since 1974, my research quest was to discover how to harness the slowest processors and how to use them to solve the most compute-intensive problems at the fastest computer speed. In the 1970s and 80s, my theory of how to build the world's fastest computer and do so with standard parts, such as the world's slowest processors, was mocked, ridiculed, and dismissed as a beautiful theory that lacked experimental confirmation. The supercomputer was a technology that meandered across physics, mathematics, and computer science. And in the 1970s and 80s, supercomputing across processors was the beautiful thread that didn't fit into the larger weave, namely the world's fastest computer that now occupies the space of a soccer stadium, and it costs 40% more than the mile-long Second Niger Bridge in Nigeria. I'm well known, but not known well. It's not known well that I discovered the world's fastest computer and did so across the world's slowest processors. My discovery was the origin of the first supercomputer as we know the technology today. On the 4th of July 1989, I saw something that's a new supercomputer that nobody had seen before. Specifically, I saw how the slowest processors in the world could be utilized to solve the most compute-intensive problems in the world, and most importantly, solve them at the fastest computer speeds. I discovered the fastest computing and explained the technology to a 12-year-old writing a school essay on inventors as a quote-unquote solving up to 1 billion mathematical problems at once and across as many processors. In 1989, I was in the news because I solved a tough mathematical problem that was then considered impossible to solve. Furthermore, I solved 65,536 mathematical problems at once and across as many processors that work together as one coherent supercomputer. Likewise, I discovered how to solve the most compute-intensive problems at the frontiers of knowledge in mathematics, physics, and computer science. Not only that, I made the first direct measurement of the fastest computation ever recorded across an ensemble of the slowest processors in the world. After my invention, the fastest computers in the world are supercomputing across thousands or millions of processors. That radical shift from one processor to 1 million processors is the most significant fundamental change in the history of computer science. I began supercomputing on a machinery that I visualized as a processor. I began programming the fastest computers on June 20, 1974 in Corvallis, Oregon, USA. In 1974, the prevailing dogma was that recording the world's fastest speed in computing and doing so across the world's slowest processors will forever remain in the realm of science fiction, and it remains a colossal waste of time. In 1989, I was in the news because I proved that supercomputer scientists who believed in serial computing were wrong. I did so by discovering how to solve the most compute-intensive problems in physics and how to solve them so that a time to solution of 30,000 years will be reduced to a time to solution of 1 day. My discovery is a new way of looking at the supercomputer. That discovery marked the date of birth of the first supercomputer as it's known today and as it's expected to be known tomorrow. Processing across the slowest processors is the lodestar technology that makes the computer faster and makes the supercomputer fastest. The partial differential equation is the mathematician's stepping stone that enabled the physicists to answer otherwise unanswerable questions. The global climate model that was used to foresee climate change derived its answers from the laws of physics that were embodied into the governing partial differential equations at the frontier of calculus. The second law of motion of physics breathes fire into the trillions upon trillions of my interlocking partial difference equations of computational linear algebra, and did so to set millions of processors on fire and to add a new meaning to the ancient Pythagorean belief that nature was numbers. My invention opened the door to how to solve compute-intensive problems and solve them across an ensemble of millions of processors, and solve them when the governing system of equations of algebra has its non-zero entries only along its diagonal. I invented how to solve many of the most compute-intensive problems arising in engineering and medicine, and solved them in parallel, and invented how to solve them across an ensemble of 65,536 self-contained coupled processors. The 65,536 simultaneously sent and synchronously received emails fired from as many processors as bullets out of my eyes that were coming from 2 raised to power 16 processors in a 16-dimensional hyperspace. My contributions to mathematics were these. I changed the way we solve compute-intensive mathematical problems. In their old way, they solved such problems with only one isolated processor that wasn't a member of an ensemble of processors. Or conversely, within only one isolated computer that wasn't a member of an ensemble of computers. In my new way, we solved compute-intensive problems across millions of processors or across millions of computers. My contributions to the science and technology that I used to discover and recover crude oil and natural gas were these. I discovered how to harness the millions of processors that powers the world's fastest computers and how to use them as one coherent machinery that emulates a super fast processor that's 1 million times faster than a single processor solving the same mathematical problem alone. One of the most difficult problems in physics was to accurately compute the flows of crude oil and natural gas flowing from water injection wells to nearby producing wells. By making the news headlines in 1989, my invention changed the way we execute mathematical calculations in the largest scale computational physics. And it changed how mathematicians solve the most compute-intensive and mathematical problems, such as those arising in fluid dynamics. And it changed how mathematicians solve them in parallel or in tandem, and solve them by distributing them across an ensemble of coupled processors instead of solving them in sequence or solving them only within one isolated processor that was not a member of an ensemble of processors. An example of the most vexing problem in physics is to foresee previously unforeseeable global warming. General circulation modeling is one of the most challenging problems in computational physics. Fluid dynamics across the Earth's subsurface gives rise to one of the most compute-intensive problems that often arise in algebra, such as the high-fidelity petroleum reservoir simulators that must be used to recover otherwise unrecoverable crude oil and natural gas. The reservoir simulation of the subterranean motions of oil and gas is one of the hardest mathematical problems. In Nigeria, the toughest or the most compute-intensive physics problems arise as triggers of equations of algebra that must be solved as a precondition to recovering crude oil and natural gas from the Niger Delta oil fields. In physics, the so-called grand challenge is defined as the field's most compute-intensive and most important problem. That compute-intensive problem is the accurate solution of an initial boundary value problem that's governed by a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations. The later equations encode some laws of physics that include the second law of motion. These laws are defined in physics textbooks and govern the motions of the oceans and atmospheres that enshroud the Earth. This system of partial differential equations is used to forecast changes in oceanic and atmospheric motions and forecast the changes in temperatures that define the global warming of the air and moisture within the Earth's atmosphere and the sea level rise in the oceans. Analogous partial differential equations are also used to hindcast or reforecast the changes in the motions of crude oil, injected water, and natural gas that were flowing inside a producing oil field that's the size of Lagos, a city of 20 million Nigerians. The typical oil field is a porous medium that's on the average 6,000 feet or 1.83 kilometers deep. Calculus is the most powerful technique in mathematics and physics. Calculus was discovered 330 years ago, but it was discovered as a textbook problem that's posed and solved for mathematics classes and on the blackboard. The body of knowledge of calculus grew over 3 centuries and 3 decades, with the first partial differential equation invented in 1746. However, the phrase partial differential equation was first used in 1845 and a century after it was invented. That body of mathematical knowledge grew over the years to become the backbone of computational physics. The partial differential equation is the most recurring decimal in the most compute-intensive problems. Such grand challenge problems are solved across the up to 1 billion processors that outline and define the world's fastest computer that now occupies the space of a soccer field. Unlike the ordinary differential equation that's defined by its single variable functions and their derivatives, the partial differential equation is defined by its unknown multivariable functions and their partial derivatives. My contributions to the partial differential equation beyond the frontier of calculus were these. In the early 1980s, and while in College Park, Maryland, I invented 36 partial derivatives of unknown multivariable functions. Computational geophysical fluid dynamics engineers could use my contributions to mathematics to more accurately forecast the changes in the motions of crude oil and natural gas that are pushed from a pumping well to nearby producing wells. And we are within a producing oil field that's up to 7.7 miles or 12.4 kilometers deep and up to twice the size of Anambra State of Nigeria. I discovered that the system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that the petroleum industry used to discover and recover crude oil and natural gas. We are missing 36 partial derivative terms. Those mathematical terms were needed to balance the system of 9 coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that are used in the energy and geoscience industries. Who needs a supercomputer? The initial boundary value problems governed by my new mathematics or partial differential equations had no analytical or exact solutions. For that reason, those equations had to be discretized and roughly solved across millions of processors under the hood of the world's fastest computer. Every oil company must use a supercomputer to simulate the perfect operational strategies for recovering crude oil and natural gas. Petroleum reservoirs simulated across millions of processors is standard operating procedure that must be used to extract crude oil and natural gas from the 159 producing oil fields in Nigeria, as well as the 65,000 producing oil fields around the world. It should not come as a surprise that the energy and geoscience industries bought 1 in 10 supercomputers, and that the supercomputer industry has a market value of $45 billion a year. Why are the 9 Philip Emeagwali's equations important? My contributions to the mathematical knowledge that's used to recover crude oil and natural gas were these. I corrected the serious mathematical errors made by geologists and physicists and made during their mathematization of Darcy's law. Darcy's law was formulated in 1856 and later enshrined into every physics textbook on porous media flows. That invention of 36 partial derivative terms is my contribution to the calculus of multi-phase fluids which flow under the surface of the earth, specifically 3-phased flows of crude oil, injected water, and natural gas flowing along 3 dimensions and across porous media that were both heterogeneous and anisotropic. My contributions were toward the applications of mathematics and toward using my new knowledge and the world's fastest computer technology to discover and recover the most crude oil and natural gas buried in the 65,000 producing oil fields of the world. Without the supercomputer that's powered by millions of processors, a significant amount of crude oil and natural gas would remain undiscovered, undiscoverable, and unrecoverable. In the 1980s, the petroleum reservoir that I simulated across my 65,536 processors served as my concrete platform and as my metaphor for all initial boundary value mathematical problems, from those which govern the traffic models of Main Street, to those which govern the financial models on Wall Street, to those govern the massively parallel processed computational fluid dynamics codes that I investigated for 4.5 decades following the late 1970s. What's my answer to the most challenging question in computer science? I invented how to solve the most compute-intensive problems at the intersection of new mathematics, new physics, and new computer science, and how to solve them by sending and receiving up to 1 billion computer codes Each computer code represents an initial boundary value problem that must send and receive data or intermediate answers to and from nearest neighboring domains. I invented how to do so across a new internet or across a new global network of processors that communicates and computes together as one seamless, coherent, and gigantic supercomputer. That's the first supercomputer, as we know the world's fastest computer today. My world's fastest computer is not a regular computer in and of itself. It's a new internet in reality. I made my invention by sending and receiving the internal boundary conditions after each time step of my discretized initial boundary value problem. And by doing both across a new internet that I visualized as my new hyperbole supercomputer, and as my new global network of 1,048,576 regular and short email wires, which were equal distances apart, and which interconnected my ensemble of 65,536 off-the-shelf self-contained processors, and interconnected them to create my new spherical island of processors. That's a new internet. Back from 1922 through 1989, harnessing 64,000 human computers, or as many processors, existed only in the realm of science fiction. Since my discovery of July 4, 1989, executing the world's fastest computing, and doing so across ordinary processors, has enabled us to incorporate previously unimaginable points of data. We did so to make groundbreaking discoveries in science, engineering, and medicine. The world's fastest computers are used to know if a new cancer treatment holds any promise, or if an untested scientific theory is valid. The world's fastest computers are used to deepen our understanding of the cosmos and know our place within the cosmos. The reason my scientific discovery of the world's fastest computing across the world's slowest processors was cover stories of top scientific publications was that it was new knowledge that opened doors into an undiscovered territory in advanced calculus, and that it opened doors into an undiscovered territory in compute-intensive algebra, and it opened doors into the unknown world where the fastest computers exist. New calculus, when discretized, led me to new algebra and led me to faster mathematical computations that were at the granite core of my scientific discovery. That discovery opened doors into the undiscovered territory of the first world's fastest computing across the world's slowest processors. In 1989, I was in the news because I was the first person to observe the world's fastest computation across processors instead of within one super-fast processor. My world record calculation made the news because it was across an ensemble of the world's slowest processors and across an internet that's a global network of those processors. That first parallel supercomputer is the precursor to the world's fastest computer of today that could become the computer of tomorrow. My mathematical grand challenge was to figure out how to harness a new internet that's a new global network of up to 1 binary billion processors that shared nothing and were equal distances apart. My contributions to mathematics were these. I figured out how to harness that new internet and how to use its processors to solve a complicated system of time-dependent and nonlinear partial differential equations arising in fluid dynamics and calculus. For the past 2 centuries, the partial differential equation was the hottest topic in mathematical research. It's both difficult and important. For those reasons, 9 in 10 supercomputer circles are devoted to solving partial differential equations. It's the reason mathematics, physics, and computer science mutually reinforce each other. Those partial differential equations are encoded in some laws of physics as prior information and therefore can be used for physics-informed simulations. Such computational physics models range from high-stake climate models to the spread of contagious viruses that might occur during a once-in-a-century global pandemic, such as the spread of COVID-19. To solve the most difficult mathematical problems in computer science and solve them across processors demanded that I reduce those differential equations of calculus to an equivalent system of difference equations of algebra. On July 4, 1989, the system of equations of computational linear algebra, which I solved across my ensemble of 65,536 processors, were too bulky and sprawling to be scribbled across all the blackboards on this earth. As a research mathematician, I started in Onitsha, Nigeria, investigating the Pythagorean triplets, defined as 3 positive integers, a, b, and c, such that a squared plus b squared equals c squared. I did so after the 30-month-long Nigerian Civil War was over. When the war ended on January 15, 1970, 1 in 15 Biafrans had died. 1 million children and the elderly died from hunger and starvation. I was a 12-year-old refugee in Biafra, the breakaway southeastern region of Nigeria. My refugee camps were in Ogidi, Oka, Oketiti, Oba, Ndoni, and Fege quarters of Onitsha, Biafra. As a mathematician searching for new calculus and new algebra, I came of age in supercomputing in the mid-1970s in Corvallis, Oregon. And as a mathematician in the early 1980s in College Park, Maryland, my obligation was to invent new mathematics and then use my new knowledge as a vehicle for discovering new physics and for inventing a new computer, a new supercomputer, and a new internet. and for creating new vocabularies and discovering new sciences that must follow: new calculus, new computer, and a new internet. Why must Africa always be at the frontier of human knowledge? If it's impossible to create a literary renaissance in Africa, and do so because of the continent's low literacy, it will then be harder to create a scientific renaissance in Africa, and do so because its low numeracy is far more daunting than its low literacy. Mathematics can only foster where numeracy is high. The lack of deep understanding of the partial differential equations of calculus that were employed to construct large-scale supercomputer models of producing oil fields is one reason European and American oil companies are paid 40% royalty to extract crude oil and natural gas, and do so from the 159 producing fields of Nigeria and through the 1,481 oil wells in Nigeria. The pyramids of Giza are testaments that Africa was once at the frontier of human knowledge. The pyramids that stand today were built 4,000 years ago, built in Africa by Africans, and built in the millennia at the forefront of human knowledge was in Africa. Africa will forever remain the least developed region if it continues to consume technologies rather than produce technologies. For 43 years following 1946, computers got smaller and faster. After 1989, supercomputers got bigger and became 1 billion times faster. They are defined and outlined by up to 10.65 million smaller and faster processors. The first world's fastest computing across billions of coupled processors that shared nothing is the most significant measurable increase in the supercomputer speed that has occurred since the programmable computer was invented in 1946. My discovery of the world's fastest computing is called parallel processing. It occurred at 15 minutes after 8 in the morning of July 4, 1989. Supercomputing across processors led to the acceptance of the new technological reality. My invention or new knowledge was this: the slowest processors could be used to compute faster than the singular custom manufactured fastest processor. Such an ensemble of processors are now used to solve the most compute-intensive problems in mathematics and science. Parallel processing was the seminal discovery in supercomputing. Parallel processing was how the fastest supercomputer was invented. I was in the news for my discovery of the first world's fastest computing across the slowest processors in the world. My discovery occurred in Los Alamos, New Mexico, USA. I jumped in joy because I was the first person to discover that the 65,536 slowest processors in the world can be used to solve the most compute-intensive mathematical problems in the world. Working together, an ensemble of the slowest processors can be utilized to address the world's biggest challenges and solve them faster than the fastest supercomputer in the world could. My scientific discovery changed the way we look at the supercomputer and changed it from the supercomputer powered by one processor to the supercomputer powered by up to 1 billion self-contained coupled processors. That supercomputer discovery put me in the news headlines in 1989. It's the reason I'm the subject of school essays on inventors. Those news headlines from my world's fastest computing that I executed across the slowest processors in the world helped capture the public imagination. Those news headlines helped to garner political support for the new supercomputer technology that can now be harnessed and used to solve the most compute-intensive problems. My quest was to discover the supercomputer solution of the world's most compute-intensive problems. Such difficult mathematical problems arise at the frontiers of knowledge in mathematics, science, and medicine. My quest was to discover how to harness the slowest processors in the world and use them to solve the most compute-intensive problems in the world and solve such problems at the fastest speeds in the world. As a mathematician searching for never-before-seen equations of calculus and algebra, and who came of age in the 1970s, and who worked at the frontier of the most compute-intensive fluid dynamics, I flaunted my uncompromising theories, and I theorized about sending and receiving emailed codes and sending them across a new internet that's a new supercomputer in reality. As my act of protest was against the racism I experienced in the 1970s and 80s, I pursued an unorthodox line of research called parallel supercomputing. In 1982, my supercomputer discovery was rejected. It was dismissed as science fiction. For those reasons, I then expected supercomputing across processors to be always rejected. I discovered that the 1 billion slowest processors in the world can be fused via emails and used to emulate one seamless, coherent, and gigantic entity. This new machine is equivalent to a high-speed processor that's 1 billion times faster. It redefines the fastest supercomputer. Parallel supercomputing is new mathematical knowledge that came of age on July 4, 1989, the day I discovered that it's faster than serial or vector computing. I established the science of fastest computing across the 7 million processors. Supercomputing is derived from parallel processing. Parallel supercomputing is my contribution to mathematical knowledge and is the invention and milestone that changed the way the modern mathematician solves his or her most compute-intensive problems and addresses some of the world's biggest challenges. The supercomputer is where the supercomputer is the scientist's best friend. Thank you. I'm Philip Emeagwali. Thank you very much.
Insightful and brilliant lecture.